Okay, I'm ready to share a screen now. Okay, thank you all so much for joining again. Um, I just updated the website, so you might want to refresh if you're at the main website, and then you should see links to the slides and the lesson. And the lesson is still, I think, a little too complicated, and I haven't described it well enough just yet. So this will be updated, but we're going to go over some of these core concepts and of raster and vector, and use as an example in the mapping lesson these ecoregions that the Northeast IEA uses, or as they call them, ecological production units, EPUs, as the polygon or vector representation that we're going to use, and grab the sea surface temperature from ERDAP and then extract for that and do a little time series plot. So that's what we're going to do in the lesson. And I just want to go to the slides, which are some old slides about just giving a background to GIS and what that means. And so this is the mapping module. And really, GIS there are different layers that you can stack and look at the relationships between them. And this was the first GIS. It was John Snow mapping cholera. So he kind of founded epidemiology and the first GIS all in one. And then a marine example I like is Ben Franklin mapping a river in the sea as a postmaster to help the Gulf Stream, help understand where the Gulf Stream is, and then ships can take advantage of it when they're going to the UK and then avoid it when they're coming back to the colonies. Anyway, fast forward, and now there's different techniques to interpolate, like in inverse distance wedding, a raster point, or getting data from satellites. And really, the nuts and bolts of a GIS historically um, is the fact that we live on a spherical Earth, and we generally do analytics and visualizations on a flat surface. So there's a lot of this stuff, a lot of GIS is really about just projecting, going from that spherical reference system to something that's planar. And fixing it in space. So I think GIS is an unnecessarily complicated word. Things are spatial. You're attaching observations to some location. Obviously, we live in a spherical Earth, so the geographic coordinate reference system, and you'll see this later, a CRS or coordinate reference system, is one in which it's taking the angular unit from the center of the Earth out to some point on that Earth and getting the latitude and the longitude. So degrees it's because it's an angular unit from that reference system. So we're not going to do a full GIS course, but suffice to say, each of these projections is just a way of taking, like, imagine a piece of paper and wrapping it around a spheroid, and which is the Earth, and then taking a light source and then projecting it onto that piece of paper. And you are always preserving. Generally, you're trading off the shape and area with things like the directionality. So yeah, and this is one way of visualizing the distortion and distance angle area with these different projections. So like a equal angle, a Mercator projection is commonly used. And there's really just two projection coordinate systems that are really extremely worthwhile. One is geographic because it's so much of our satellite, our GPS and our referencing system is based on this geographic coordinate system, and particularly a certain datum or flatness to the Earth called and there's a number to it, 4326, which we'll see in the lesson. And then there's another one, which is using the web Mercator, which has all these flippy maps for being able to show different base maps. And that's 38 something. I'll pull up the number in a bit. But Mercator was used to get directionality. So in the nautical days, where maps were most commonly used, that made a lot of sense. But it really distorts the hemispheres as you approach the poles, because each square of latitude is actually getting smaller as it approaches a zero area at the very pole. So this is over here, another common one used for more global analysis, like mall-wide. So, and then there's compromises between area, shape, and angle that you'll see. And that's a fun video from West Wing back in the day, talking about the biases that these things give. And yeah, here Greenland looks way more massive in Mercator than Africa, but actually Africa, you can fit all of Western Europe, some of Eastern Europe and China and the US in there because of the distortion. And then geodesic lines. This used to be a lot more tricky, but now it's more baked into just doing basic spatial analysis, where if you want to look at the straight line between two coordinates, you want to account obviously for the spherical Earth. Yeah, so let's just get into, we've already been talking about tables with how to manipulate data. And then this is more of an Esri or ArcGIS view of how the little icons they use and the names they use. But there's sort of these feature classes is what they call them, but or more generically, points, lines, and polygons. So points, you can sequence points to construct a line. You can enclose a line to then construct a polygon. And polygons might be made up of multiple polygons that describe holes within. And then raster is the pixelated image that you might take. So they're two very different data types, but you can represent them and interchange them and extract one from the other, as we'll do in the lesson. So vector and raster, I kind of like the expression vector is corrector, but raster is faster. So you can be very precise about where those points live with reference to the Earth with vector, whereas usually with the raster, each pixel has an equal width and height. So whatever the resolution of that pixel is the finest, most finely resolved of the features that you're trying to describe. So vector can be corrector, but raster can also be high resolution. But it's just that when you do the rasters, this other thing you can do is map algebra. So if you have pixels one on top of the other, you can do little tricks to add them, subtract them, multiply them. And if they're aligned with each other, that's super fast, rather than having to figure out which polygons overlap which polygons and do all that geometric calculation. So that's why raster is faster, or can be, I should say. And then we can relate each of these features, whether it's a given polygon or point or line, if it's vector, or if it's a given class or pixel value, like a land cover or a seascape class, if it's raster, one to many with a table. So yeah, so we can have points, lines, polygons. Let's not worry about annotations, and then these can be multiple constructed. So each feature can have an associated row in a table with attributes. Yeah, which we'll see in the lesson. And you can actually connect these points to lines with some bendiness, let's just say. And then when you're thinking about vector and raster, it's good to think about tolerances when you're performing operations. Sometimes that will be an argument in some of these functions. And shapefiles, which are most commonly used, don't maintain topology, but it's more of an advanced topic. So yeah, raster is faster, the vector is corrector. And the idea is that you have, let's say, different classes, like this is water and grass and some trail and some forest and some sand and some buildings. And the vector representation would be this, where you're describing points that connect the lines, that describe the polygons that enclose what we're seeing. And then this would be the raster or pixelated representation. And so a raster is just really just a matrix of values that get stored, and there's different ways of reducing the size of that storage. So a tagged interleave format, or TIFF, is the most common, and that compresses a repeat of sequences. If you use something like a JPEG or a PNG, those can actually take the original data and to optimize the file size, distort those values for visual. So TIFF preserves the original values, and that's why it's the most commonly used raster format. So you've got the cell size that repeats, and that's the grid topology, meaning like the overall structure, how many rows, how many columns, what's the starting point in X and Y, and the rest is just populating that grid in some consistent way with a bunch of values. And so, yeah, a lot of different uses for it. And of course, you can have bands like red, green, blue to then describe an image that is on the visual spectrum. But you can also have bands or a stack of arbitrary values that has the same topology, which we'll also do in the lesson. And this is a bit dated, but yeah, there's a lot more. These are the most common spatial packages as of a few years ago. But SP was this spatial original vector package. And then that has been superseded, I would say, by this SF package, which is the spatial features package. And raster is the package that can read and write in rasters. And leaflet is what is an HTML widget. So we talked about that during the visualization module, and that's just means that it's made for HTML visualization, and it takes this leaflet JavaScript library and then allows you to create interactive visual interactive maps with your data using leaflet. And then ggmap is a ggplot library that allows you to add some of the tiles that you'll see with this other mapping. So with that, I'm going to go into the training module for the map, so you can navigate here to the lesson. I'll add the menu item too. I was having trouble simplifying some of this stuff, so this is not fully fledged, but we can talk about the concepts, and you can see the raster and vector representations, and some of the trickier parts. Hopefully you can still grasp the concepts, and then I'll try to explain more with comments and description in this module when you revisit it. So let's go into this, and I'm going to look at the R Markdown, and what you can do is actually, you know what? I'll do it in the way that I'm recommending. So I'll take this R3 exercises.rproj and I'll launch that. So that's what you guys should be doing when you're trying to repeat this. And here we can see I could just copy this from the last time and do, if I just do file, new file, text file, it's just a generic thing, so I can copy paste, and then I can say map.rmd. The point is that you want to start with a map, an R Markdown file, and yeah, this is actually all I need, and that's just pretty basic page when I knit it. And now I'm gonna go ahead and start in. So this is this map RMD. And what we're gonna do is create chunks of our code. And then I'm gonna talk through what's going on here. Okay, so let's create an R chunk. And
Hey Ben, it looks like we can't hear you right now. Can you hear us? Still can't hear you. Looks like you're muted too.
oh, wow. Okay, sorry about that. I was trying to move the chat. Can you hear me now?
Yes, we can hear you now.
Okay, cool. I was trying to move the chat window over, and I think that's what did it. Times past, I've bumped my headset. Okay, so there's this little trick. So if I have some non-existent library, and it's like there is no package called some non-existent library, um, so it just errors out. And if I use this require, it actually what it does is it doesn't error out. It gives me a result of false. And so there's this little trick. There's this library I really like called librarian because it has this one little helper function called shelf. And what shelf will do is it will install the package if you don't have it. And so to get the library package, so this should work if you don't have librarian, this would return true because I say exclamation, say not. So if not true, it would be false. So that's why. So this is true, so this is false, so this does not get evaluated. But if require is false, meaning you don't have it, then this is true, and then this gets evaluated, and it'll install the librarian package and then load it. Otherwise, this would actually load it. This is like library. So anyway, this is the little trick to install librarian if you don't have it. And this is the librarian shelf function that not only installs a package from CRAN if you don't have it and loads that library, but here's a little trick is that it can, if you give it the owner, GitHub owner and repository that we talked about in the collaborate lesson. So always with GitHub, the first part is the owner and the second part is the repository. So we can go to github.com/Noah edab ecodata and see this is this awesome package that the Northeast IEA has made to do a lot of their report generation. And you can install this if you don't have it, or just load it if you do. this way. Now, one other thing about this librarian shelf function is that if you don't have the latest version, you might get this error. GitHub has been doing a lot of annoying changes lately. So you need the latest package. You can always go to the packages pane and look up a given library and see what version it is. So, and you can always click on update in the packages pane, and it should have a sorted list. So you can see which ones need to get updated from here. And you can select the ones you want to update and update them. Okay, so that's just loading packages. But let's get back to getting some actual spatial data. The reason that we got this eco data package is that we want to get the spatial data. So let's add another little chunk. And so I've referenced this before, but you can reference a package, and then you can do 2 colons. And this is a way of explicitly, generally you're referencing a function. But what's interesting is that packages can have data sets loaded into them. So this package has an ecological production units data set. Now, if you want to see just what all the data is for a given package, you can use this base data function, and it'll actually show you a list of all the data. And you'll notice that it's not in it's not in my environment, but I could just reference EPU SF and it shows up because it's sort of invisibly available. And a lot of our examples use these data sets that are loaded into packages within their examples. And when we look at this EPU SF, we see that it's a simple feature. So that's coming from that SF. And there's even this, I can do F1 or type question mark and send that to the browser or to the console and look at the help. And we can see the help in the package describes what this is. And this is this SF or spatial feature object. And I can also say, okay, what is this EP SF? Okay, so it's a data frame and it's a spatial feature object. So this extends the data frame, and the geometry for the polygons are here, and that's described by an XY coordinates of points to then describe that polygon. And then here's the data frame, these columns, EPU, shape length, and shape area. Okay, so it's also got this coordinate reference system of NED83. So it's actually a geographic coordinate system, but because later we're going to use some ERDAP data that's in the has a different datum, and that's another GIS topic that's kind of, it's just like the wobbliness of the Earth, different ways of describing that. And so we can transform, which is projecting that data into World Geodetic System 84. So North American datum is specific to North America. This is World Geodetic. This is what all the GPS satellites use and what a lot of other geographic data is in. And sorry, we don't have too much more time to talk about that. It's its own sort of topic, but here's that CRS, that coordinate reference system. So we use the dplyr style of this pipe operator. So what's on the left, we're feeding to the right. And so the second argument is the CRS, the coordinate reference system. And that's, we have just this little helper number of 4326. So that's how to project data. And if you just want to look at one of these geometries, for instance, you'll notice that it's actually it's its own list of polygons inside of it, and we can plot this out. And what it's showing then is the representation of each of the columns. And if we want to specify a column, we can reference that inside that object. What did I do wrong here? There we go. And another thing I like to do sometimes when I'm knitting, I find it kind of annoying that it shows up here and I kind of want to see it over here in a different window. So you can change that in the gear icon to chunk output in console as opposed to inline. And so I can remove that output and then I can just make it show up over here on the right in the plot window. And here we see that these are the codes for like Georges Banks and some of the others that were mentioned in the help that we referenced before. So Georges Bank, Gulf of Maine, Scotian Shelf. Okay, so that's a basic object, but where does this thing live in space? So where in the world is this? And there's this package called MapView, which is probably the quickest way to interactively plot your data. So let's load that library and then use the main function MapView. And what's nice about this is that actually I can click on the given, it not only shows a background map, but I can click and I can zoom in and out. So now I'm in the viewer, which is the HTML viewer, not the static plots pane. And I can see the attributes for that feature here. So we see that EPU is the main thing that we're interested in per feature. And really, map view is just a wrapper around, let's add another chunk. It's a wrapper around this leaflet package where you can get a lot more fine-tuned control. So with the leaflet package, I'm just going to comment out this more complicated line. And I'll just run this. So this is a basic interactive map. We don't yet have data. And then there's all these different functions for loading data in. You can add all kinds of stuff into your map. And let's add that data. So add polygons has a data argument, and then we can just add that. And we get something similar, but it doesn't have, we can zoom in and out, but it doesn't give you that option to click on the, with the pop-up. You'd have to make that yourself, but you can customize it with the leaflet app. And there's another, this is the default base map, but we can actually change the provider tiles here. There's a whole monster list here. I can type providers. This is another data object or list object that comes with the leaflet package, and you can see all these guys here. So one I like is the Esri Ocean base map, and we can plot that. So as you zoom in, it actually, the Esri Ocean base map says Hudson Canyon. Now, these Slippy maps, these tiles in the background, they're just images that get served to this browser based on the zoom extent that I'm in. So it's not the data. We're not actually rendering on the client all these features and doing the shading on the bathymetry. That's all pre-rendered, but it's a really nice background for spatial reference that we can use, and also good to kind of background check. So let's now say what we want to do is let's say what we want to do is get sea surface temperature or some raster data extracted for this extent. Well, we can go to one of these ERDAP servers, like Coastwatch is one of the main ones, And you can search there for things like, let's say, SST or temperature. And there's a whole bunch of data sets here available. And one that I like and that the R ERDAP package, which is what we're going to be using, references is this JPL. So this is a multi-scale, ultra-high resolution sea surface temperature analysis that would be in this somewhere in this list. And this is the ERDAP way of grabbing it. See, with ERDAP, you can filter based on the time period of interest, and you can filter based on the latitude, longitude. So we can use an R ERDAP package to specify the bounding box for this these spatial polygons of interest, and then extract that bounding box and get that data. So let's do that by degrees, and let's add another little chunk. And we're going to use a couple packages here. We're going to use the here package to get a reference to where we're going to save the grid DAP output of sea surface temperature as a R data stream. So this is like a native way of compressing any R object and then saving it and then loading it back in the future. And that's sometimes the ERDAP servers get overloaded. And so this is a way of caching that result and then saving it and loading it for later. So anyway, so this is just a path right now. It's just a character string to give us a path. And that would be specific to your repository. And so it's making it portable for if somebody else runs this code with your repository, then it'll work on their file system too. And this ST bounding box, so this is from the SF package. And you'll see there's ST underscore bounding box. And actually most of the functions in the SF package start with ST. And the reason for that is that it's kind of historical. PostGIS, which is the most popular spatial database connector for Postgres, it started off with ST for space-time and prefixing all of its core functions with that. And so SF borrowed a lot of those functions in meaning, and so they start with this ST. So this ST bounding box is going to give us that bounding box that gives us a latitude, longitude bounds by which we want to extract from the ERDAP server. And so we can just run that function on these spatial features, and then we get this bounding box. So xmin, ymin, xmax, ymax. Okay, cool. And now we're going to actually start using this. So here we're getting a bounding box. We're getting get path for feature caching. And then here we're going to get some ERDAP dataset info. So this has the same ID, and it defaults to using that ERDAP server. It can actually be it can be any ERDAP server. It's free software that you can install on the server to serve data, and it gives you this filtering capability and transformational capability. Really powerful server. So we can look at this information, and what it's saying is that this corresponds to this data access form, time, latitude, longitude. So we see that time, latitude, longitude. And then there are these other variables, SST, the number of observations, and the sea land mask. And that SST has these units of degrees Celsius. Okay, cool. So with that info object, we can use this other R ERDAP function. And we're going to wrap this in a little caching. This is another little trick where, okay, so this file that's from the path we defined earlier. And does this file exist? It does not exist. So if file exists is false. So using the negation, that's going to be true. So now we can go use this grid-dap function. This is a powerhouse function that takes that info object from above, which just says like where to go form the URL, and use this API to access that data. And we're going to want to get that SST back, and we're going to specify the last year. So I knew from that grid here that it's referencing based on this on the 16th of each month. And so we're going to specify the last year. And then we're going to use that bounding box to get the min and max. So we can see these fields here, and the RERDAP, which I reference here, there's a lot of nice documentation in this package about how to use it and specify latitude, longitude, etc. So I reference that at the bottom of this lesson for the reading. And so now we're going to go get it. So I'm just going to run this line. So it's going, and ERDAP actually does this thing where it federates data. So this is where this is the ERDAP server in which it actually lives, but that other server that we were looking at can display the information and inform the request for you. So we have now SSTGD. So let's see what this looks like. Well, as opposed to the SF object, which had a geometry column, this is actually just a simple table. And it's got the time, the latitude, the longitude, and the SST value. And here we see there's about 13 million rows to describe that boundary in that period of interest. So it's slicing that data. And in case the server down, for whatever reason, we can also save that object into our local file system. And we can just take a look and see how big that is. And the path is here, data, SSTs. So it's 29 megabytes. Anything over 50 megabytes, you'll get a warning if you save on GitHub saying it's kind of a big file. And for free repositories, there's a maximum limit of 100 megabytes. And usually a free repository has a maximum of 1 gigabyte total. So 1,000 megabytes that you can store. So careful with bigger areas. You might want to save it outside of your GitHub repository. And then you can read it in. So this is going to overwrite. Save RDS and read RDS are base functions for reading and writing individual objects and then saving them back. And you can see that it's an ERDAP grid DAP object. So just like the SF extended the data frame, this ERDAP is basically extending the data frame and adding some ERDAP metadata associated with it. Okay. Let's see how we can actually plot this now that we have the data. So the other thing, if we take a closer look at this object, you see that it's got these names of summary and data. So it's a list object, basically. It says large grid dap, and I can expand this here and see that there's going to be the summary object, and then there's basically this data object. And so the data is where we're going to actually use this data and use ggplot. And instead of the geometry type of like the lines and that we did last time, we're going to use a geometry of type tile to actually plot it. So let's use that. So now we're going to plot it, and so we're going to do some data wrangling. So we're going to use the dplyr library. We're going to use ggplot2 package, and we're adding a new package here with this shell command called mapData. MapData has a mapData function. There's a world in high resolution, and this is how we can get the coastline. Now, if you look at this function, there's different arguments, and then ... this ellipsis means that any additional arguments are passed to this function. And then here you can see L4, so you can look that up and see how that works. But this is going to trim the coastline to our bounding box X and Y limits. So we're going to get that data, and then here we grabbed the whole year's worth of data. But if we just want to plot a given month, like let's just get the most recent time, we can use dplyr's filter to take that data object and get the most recent time. So this is just going to have just one time time value of this, and this is actually just a character string, but we'll figure that out next. And so this is really just a simple table where we've got lat, long, and then SST, the value, and it ranges from 9.6 to 27.2 degrees Celsius. So we're going to feed this data frame into the X and Y and the SST. The geom polygon it's going to pull that from the coast object we created, and it's going to use the X and Y here and fill it in with gray. So we can look and see just what that looks like in the plot pane. So that's just getting, even though the ggplot object, we gave it the data and the aesthetic that we talked about last time, we haven't, this geom polygon, we fed it some specific data. So we haven't actually plotted the data that we want here, the sea surface temperature. Only when we have the default data argument. So geom tile is like little rectangles. And now that's going to actually plot the data. So remember, ggplot, we talked about with the visualize module, is a layering. So we want to specify the coastline below so we can see the sea surface temperature tile geometries above. And I think I have to give it this. Yeah. So now we can also, this is the default color ramp, and we can update that to being, our ERDAP comes with a bunch of colors that, color ramps that are useful for plotting marine related things. So if I say names of that colors object, you'll see that there's like CDOM, oxygen, salinity, velocity, temperature, oxygen. So those are kind of nice. And then we can, and this is mostly code from the RERDAP documentation. And we can update the theme so it doesn't have that background default ggplot gray with the white bars, and then give it a title and change the X and Y labels. And yeah, and now we've got a static map that could be in a report, PDF, or a Word doc, works well. If you have an HTML widget that's normally used to rendering to an interactive plot, like a leaflet, R uses this other thing called it basically takes a snapshot of that image and just embeds that in. So that's for a static plot. So let's do, this is a static plot. And now let's say that we want to, and this is where it starts to get a little tricky. Let's say we want to extract the SST for this raster time series. So the first thing we need to do is actually convert it to a raster. ggplot likes things in tables, and it can plot things actually quite nicely in that, and that works, but we need to convert this into a raster. And this is where we're going to use a few more tricks. And I welcome other feedback. Okay, extractomatic, yeah, nice. That's a good one. Cool. All right, so here we go. Let's grab this stuff and I can explain it. Okay, so this, we're gonna use a list. We're gonna do some fancy manipulation here of the data to get it, wrangle it the way we need it. So if we look at this, that data object we had before as a tibble, there's something a little slightly funky, unfortunately. Latitude and longitude, if we get the unique values, sort it, and then look at the differences, they don't, there's a slight mismatch in the widths. So rasters like to have equal width and height. And so we're going to round things to actually being 0.01 rather than this, there's like this tiny infinitesimal little fractional difference between some of those cells. So it's described as a 0.01 degree data set. So we're just going to round these. And then we're also going to convert the time, which you see here is character, and we're going to convert that into a date. So this uses the format where it's expecting the year, the month, the day, and then this is just some text because it's not preceded by a percent saying it's a special value that you want to use. And this is a way then of converting the, a character to an actual date. And then once we do that, we can drop the time by selecting minus time. And then we can filter out all the, right now we have 13 million rows, and we can reduce this to something much smaller. So that's just an initial little cleanup. Now, the really tricky thing is once we've done some really simple cleanup, now we have only 8.8 million rows. That's just the actual data. We've simplified our rounded up our lat and long. So now we're ready to convert each date or month, really, because this is a monthly raster, into its own raster. And we're going to use this feature I showed with the manipulate lesson called nesting. And when we nest, we say, okay, the data, we're going to put an entire data frame into its own cell. And we're going to, any column that is not in this data frame will then be what uniquely identifies each thing. So each row. So when we look at this, we go from 8.8 million rows to now it being unique by that column that I did not include in the data, which is date. So now we're down to 13 rows. So that's for each month. And then this is the entire raster data for that month. So here's where it gets, this is like a fairly advanced topic, but it's the right tool for this task, which is converting each of these months into its own raster. And we can use this per map. And this is not map as in the mapping that we've been talking about so far, but this is mapping as in crosswalking one element to the next. And this is going to crosswalk each cell of data into this new function. And then the default for map is to return a list type object back. In this case, it's going to be a raster. So this, let's just run this because that's a lot to take in all at once. And then we're going to actually dive inside that little function that we create here. And this could take any function, but this is what's called an anonymous function, where I'm not naming it, so it's anonymous. And this data gets fed in here. It's the first argument, and it's just called x inside the function. And what we get back is a raster layer. And we'll see what that means and what it looks like in a second. But if I want to see like, wait, what is going on here anyway, I can turn on a browser command inside of this anonymous function. So a function in R is defined by, normally you'd say, actually I could do it like this too. So I could make it not anonymous. So, so table to raster. Maybe this is my little function. And then I could just, the mapping, I could have done it just like this. And if I comment that out, so this is creating a function, and it says the first argument is x, and then do this stuff, and we get the same results back. And then I'm going to do a little browser, which stops the execution of code and then lets me inspect what's going on inside of a given function. We'll let this finish. Okay, so just so you can see that that gave us the same result, there it is. And now I'm going to redefine it. I'm going to define this. You can see that if I spit this back out, here's our little function. And then I'm going to run this again. And because it's got this browser call inside, it stops execution. And now I can get inside there and be like, okay, what is X? Well, this is the tibble, just the lat long SST for that date or month of interest. And then you can use these, there's probably a few different ways of defining this. And this is, SP is the old spatial object that raster liked the most for converting it, SP to raster. And so this is now, if we look at X now, it's a spatial points data frame. So it's basically just saying, now make that a spatial object and then make it gridded. So now it goes from a spatial to now it's an actual like a gridded, a spatial pixels data frame. And then raster, the raster package that can convert that to an actual raster layer. So if I did this, let's see, if I did, so let's say y equals that. That's the last thing to operate. And then I plot this y. This is the default color ramp for that, for raster. And now we see that visualized. So let's stop the execution inside this function. And that was just to demonstrate how that works and creating a little function, getting inside there. And this raster stack, so a raster layer is a single raster, but we have multiple months, so we can make a stack of rasters. And by feeding it that raster, these raster layers. So now we've got this raster stack, and then we can update the names to being the dates. And so far, this raster stack, so I prefixed it with SST because it can't be a number, otherwise it adds an X. And it doesn't have a coordinate reference system, so we can define that like this with the raster object 4326. And the rest of this is basically just manipulating that, well, I'll just, this is, so far we've just been transforming that extracted ERDAP table into an actual raster stack that we can then use this extract from. So this raster extract takes an X and a Y. So a raster object, meaning a layer or a stack or a brick. I won't go into that. So no, it's like a stack. And then you can feed a Y, which could be a points, lines, polygons. And more recently, it allows you to use spatial features and not just SP objects. So, and then we feed it a function so we can get the mean and the standard deviation. And whenever there's NAs, we can remove it. So the point is that within each of those large polygons that we previously had, we can then get an average value within them. So we're looking at both the polygon vector data and we're looking at the raster data, and then we're summarizing for each month the mean value within. So we can run these functions to do that. And I know we're at the hour. I'm almost done. And I wish there was a simpler way to do the rest of this. I think there might be. There's a tidy raster package that I might see if simplifies this next set of steps. Because this raster extract, it's not the friendliest format it returns. It's in a matrix, not a data frame. And so we see that each row corresponds with each row of our spatial features, our polygons. And each column corresponds with each of our raster layers. So we want this, but then basically to plot it as a time series, we need to transform it quite a bit. So, and we need to combine these two things if we wanted to show a standard deviation. So we can take this guy, convert it to a tibble. Okay, so now we have a tibble. And then we want to add this EPU sequentially, and then maybe add a statistic for mean. So now these two are what are going to uniquely identify each row, and then we want to pivot it. So right now it's wide with each month in the column, and we want to go long, so we can pivot. So then we get, so now it's long, and now we get this month here. And we can do the same thing with the other one, and then row bind them together. And then we can replace that SST. If we just drop that out, we can convert it to double. And now we've got date. So let's remove name. And now we've got EPU stat value date. And in order to use the digraph, it actually likes it wide based on each series that you want to plot, you want as a column. And so now we can do this. Yeah. So stat still would alternate there, and that gives us what we want. and then we can actually plot it. Okay. I forgot to run this to define that. And now can use the digraphs that we showed last time to generate this. So I don't know, something looks a little funky there. I think I need to go back and look at this. I'm going to revise this within the next day or two, tops, and update the lesson. But apologies for not having this more described. That last part got a little tricky. Lots of little tricks and packages and functions here. It's just really scratching the surface of what you can do. And yeah, I think we want to open it up to comments and questions. And maybe I can start. Kim, if you want to direct me, I'm looking at the notes. Andrew Thompson mentioned the extractomatic, which is really cool. Yeah, and we go to Roy Mendelssohn's page here. Yeah. So I haven't used, I don't know all the latest with this, but it looks, that might be a good ticket to try this out. Okay, and I used the code gallery. Awesome. Yeah. So this might make it a little easier. Cool. I like it. And then there's a comment that the map is missing some land features, such as Long Island. So let's see with that plot. We have the coastline. That might be a problem with just how this clips with this L force option. Yeah, there are other ways of getting coastlines that might be better.
In the EcoData package, there is a spatial feature called Coast that is the one that we use for the daily ecosystem reports. And I think that one includes Long Island and other, islands and stuff off the coast. But yeah, there's a million ways to get polygons and of the coastline in R.
Mm-hmm. Yeah, you've got this coast shapefile that you load. Yeah, and I should have, you can use read underscore SF. So yeah, just as like an example, since this, see, I don't know if, oh, I think I forgot to load these objects. Should have gone over basic loading of shapefiles. So like let's say package
Looks like someone asked, could it be because the data are plotted on top of the polygons?
Oh yeah, thank you. Yeah, that's more likely why. Yeah, yeah. So if these smooth pixels over the top, then you wouldn't see it. Yeah, thank you. We could also add transparency to the plot to like the pixels and maybe see the difference. So let's see. You add There's a alpha value usually to add transparency. But, I don't know. I'll look into that. So thank you for flagging that. It's a good. We'll see if the SST data is there, and I'll add the transparency and see if strangely where it shouldn't be. Yeah.
And there's a request for a little demonstration. It would be helpful to show how to load a shapefile and how to create rasters from them, or maybe that's in the lesson.
Yeah. Let's see. Trying to remember how to get the path of the package. So I'm spacing out on. I don't know if data raw is. So let's see. Good data. So I worked on this a little bit. So I should have a local version of this. And then I'll get a path to some shapefiles there that you were just talking about with the coastlines. So this isn't going to work for yours, but I'll figure out the other way to do this. So this is kind of nice too. You can just start typing a path as a string and it'll autocomplete. So I want to get the data raw, and there's some coast, or it was under a GIS folder, and there's some coast data. And you can reference that the dot shapefiles have multiple files. The dbf file, .dbf is the table. The dot shape is the spatial features, and there's a few other dot names, but we can use this as like the shape. And then with the SF package, you get a read SF, and you can just enter in that shape. And then we've got some northeast coast that we're reading in. So yeah, just I'll use a consistent name here. And then if we plot that, so just like you can read underscore CSV, you can read underscore SF. They try to keep that similar. So you can also similarly write, and you can write as a shapefile, or you could write that spatial features object as something more like a GeoJSON. Like if I used here, data northeast coast GeoJSON. That's what GitHub would understand a GeoJSON file and give you automatically a map preview of it from GitHub. Yeah, so there's different formats that the SF package can write. I think it's a fairly complex coastline because it's taking a while. Yeah.
There is also a question about adding a scale to the map and like a border like the ones from QGIS.
Right. Yep. So that would be with the ggplot one. That would be with adding a legend. So let's see that. So that legend got added automatically here. And are we talking about adding other legend items, maybe?
I'm guessing they mean like a distance scale, like
Oh, a border scale. Oh, yeah, yeah. Right. Yeah, scale bar. Yeah, the GG map library, which, sometimes this gets a little funky. Sorry, I think it's hung up trying to plot that coast. Try to close some other stuff. Let's just stop that. Yeah, there is a utility function in ggmap to plot scale bars and north arrows. So that's what I would use for the static. And in the leaflet, so if you go to the RStudio leaflet help, they talk about there's all these other kind of nice little additional features, including here's even a measure feature, so you can you just say add measure. Here's how to change where that is. You can add graticules. You can even add this terminator, day-night indicator. This is also a common thing, is to show an indicator map, and that's even expandable and collapsible in leaflet. I thought there was a scale bar, but maybe it's just the measure. There is a... Yeah, I think there is a scale bar for this that you can add to a leaflet map as you change scales too. Okay, gosh, this thing is really hung up.
Yeah, I don't know why that's so angry, but I can fix that. There is a question about example. There's two different scaled maps on the same plot. How do we work those out for like a big map and a small map?
I think that question is talking about an indicator map, because these would be two different scales that they're zoomed in. So it's okay. So the indicator is showing you where in the world it is, your zoomed in version. There actually is another fairly cool little feature, another mapping feature. If you want to show multiple maps of the same thing and then compare them, I think I did this with somewhere down here. No, not Cut Coffee. Shoot. Sorry, wrong one. Hmm. Where did I do this for? I was comparing some coastlines, and I had to show 4 different panes of the same map, and they actually can synchronize together, which is quite cool. And that was, I just have to find the library, where I did that. I'm forgetting where that is. Sorry, I'll get back to you on that. There's a cool, it's with the map view sync. Leaf sync, yeah. I keep on changing the names of things, but this is the package. So you can get these 4 different panes, and as you zoom into one pane, the other pane also zooms in. So you can show any spatial data on there. And see, there's a little scale bar down there too.
There's a question about bathymetry. I used to like using ggmap to bring in bath images for background, but last I checked, they want a credit card info. Is there a recommendation for bathymetry background maps?
Bathymetry background. So the raster function, a raster package actually has this like get data function. Let's see if I can open up my exercises again. So the raster get data. And one of the data types is the SRTM, which is this space shuttle radar topography mission. You can actually you can use this get data and download some 90-meter resolution data with this raster get data function. There's another one that's the MAR map. Is a package to help with getting and using marine mapping data. And as far as globally available, GEPCO is, this is what it helps with, and that's probably the best package for getting bathymetry. And yeah, that should all be free for getting bathymetry data. Yeah. Cool.
Looks like that was all the questions. The rest is just people helping each other out, which is awesome to see. Does anyone have any other questions for Ben? Don't see anything else coming in. So thank you so much, Ben. I'll copy the chat and send over the recording once it's finished.
Yeah, okay, great. And I'll update this lesson since it's woefully absent of description. And then next time we're going to talk about reporting techniques. So that's going to be then taking pretty much everything that we've been doing and then how to put this into online and interactive reporting formats. And we'll go over creating some basic HTML like dashboards and then even automatically rendering things with GitHub Actions. Okay, well, thank you all so much for attending, and feel free to reach out if there's anything else that you want to see. And yeah, I look forward to seeing you next time. Thank you.